In Chapter 4.4, we are introduced to the topic of compound angles. For this presentation, we will first go through the different compound angle formulas for sine and cosine. Secondly, we will see how to apply the compound angle formulas in order to determine exact trigonometric ratios for angles that can be expressed as either the sum or difference of special angles. Over here, we have four basic compound angle formulas involving sine and cosine. The first formula is sine x plus y equals to sine x cosine y plus sine y cosine x. The second compound angle formula is sine x minus y, which can be expressed as sine x cosine y minus sine y cosine x. The third compound angle formula is cosine x plus y, which can be expressed as cos x cos y minus sine x sine y. The last compound angle formula, which is cos x minus y, can be expressed as cos x cos y plus sine x sine y. Right now, we will see how we can use an appropriate compound angle formula to determine an exact value of cosine 11 pi over 12 and tangent 5 pi over 12. For the first question, we are trying to come up with a compound angle formula to determine the exact value of cosine 11 pi over 12. By looking at 11 pi over 12, we can note that it can be broken up into cosine pi minus pi over 12. By applying the compound angle formula for cosine, we can express this as cosine pi over 12 plus sine pi over 12. From looking at this expression, we know that cosine pi is negative 1 and sine pi is 0. Since sine pi is 0, we can immediately omit this expression. Right now, we just have to deal with cosine pi times cosine pi over 12. However, if we look at cosine pi over 12, we will note that we have to break up pi over 12 into special angles to work with. Hence, this expression can also be simplified into cosine pi times cosine pi over 3 minus pi over 4. In doing so, we have broken up the angle pi over 12 into the difference between pi over 3 and pi over 4. From here, we can apply the compound angle formula to derive another expression By applying the compound angle formula, we will get cosine pi over 3 cosine pi over 4 plus sine pi over 3 sine pi over 4. From looking at this expression, we can see that the angles are now special angles, and hence we can derive exact trigonometric ratios for them. By simplifying this entire expression, we will get cos pi, which is negative 1, multiplied by cos pi over 3, which is half, cos pi over 4, which is 1 over root 2, plus sine pi over 3, which is root 3 over 2, times sine pi over 4, which is 1 over root 2. When we simplify this expression, we will get negative root 3 plus 1 over 2 root 2. And this can be further simplified into negative root 3 minus 1 over 2 root 2. For the next question, on tangent 5 pi over 12, we are trying to derive the exact trigonometric ratio for this expression. By looking at this expression, we know that this question is slightly different as it does not directly involve sine and cosine. However, we can change this into sine 5 pi over 12 over cosine 5 pi over 12. The reason we can do this is because sine over cosine gives us tangent. From here, we can apply the concept of compound angle formulas by dividing 5 pi over 12 into the addition of two special angles. We can do so by changing 5 pi over 12 into the sum of pi over 4 and pi over 6. The same thing goes for the denominator, which is cosine pi over 4 plus pi over 6. From here, we can express both sine pi over 4 plus pi over 6 over cos pi over 4 plus pi over 6 into another expression using the concept of compound angle formulas. This expression can also be written as sine pi over 4 cosine pi over 6 plus sine pi over 6 cosine pi over 4 over cosine pi over 4 cosine pi over 6 minus sine pi over 4 sine pi over 6. By looking at this expression, we can see that all the angles are special angles as there are exact trigonometric ratios for them. Hence, we can simply substitute in the values and get 1 over root 2 times cos pi over 6, which is root 3 over 2, plus sine pi over 6, which is half, times cos pi over 4, which is 1 over root 2, over cos pi over 4, which is 1 over root 2, times cos pi over 6, which is root 3 over 2, minus sine pi over 4, which is 1 over root 2, times sine pi over 6, which is half. From here, we can simplify the expression into root 3 plus 1 over 2 root 2 over root 3 minus 1 over 2 root 2. By simplifying this expression further, we will get a final answer of root 3 plus 1 over root 3 minus 1. In chapter 4.5, we are introduced to the topic of proving trigonometric identities. There are two different kinds of proving questions which we can encounter in this chapter. The first is to show that the left-hand side is equals to the right-hand side. The main types of questions that we will encounter are questions which involve the use of compound angle formulas. Secondly, there will also be questions which require us to apply the concept of factorization. Thirdly, there will be questions which require us to multiply the numerator and denominator by a common term. Of course, with proving trigonometric identities, we actually have to use all the concepts from chapter 4.1 until 4.4. The second type of questions which we can encounter is to show that the left-hand side is not equals to the right-hand side. In other words, we are trying to prove that a trigonometric identity is not an identity. We do so by using a counterexample, which is to let x be of a particular value, followed by evaluating the left-hand side and the right-hand side, and finally showing that they are not of equal value. For the first question on chapter 4.5, we have a question that is asking us to prove that sine 3x is an equivalent expression to 3 sine x minus 4 sine cube x. We start with the left hand side by writing left hand side equals to sine 3x. From here, we break up sine 3x into sine x plus 2x. By looking at this expression, we know that this question requires us to involve the use of compound angle formulas. Hence, we can apply the compound angle formula for sine x plus y, which gives us sine x cosine 2x plus cosine x sine 2x. By looking at this expression, we can see that right now we have two double angles to deal with. The first being cos 2x and the second being sine 2x. Over here, we have the double angle formulas for cosine 2x and sine 2x. If we look at cosine 2x, we can see that there are three different expressions for it. The first is 2 cos square x minus 1. The second is 1 minus 2 sine square x. The third is cos square x minus sine square x. How do we decide which one we are going to use? If we compare the right hand side, we can see that there is no cos being present, there is only sine. Hence, we should choose an identity that does not have any cos, which is the second one. By putting in the second identity into here, we will get sine x times 1 minus 2 sine square x. Right now, we just have to substitute sine 2x as 2 sine x cosine x to continue this question. By simplifying this expression, we will get sine x minus 2 sine cube x plus 2 sine x cosine square x. Once again, if we look at this expression, there is a cos square x here. However, on the right hand side, there is no cos being present. Hence, we can get rid of the cos square x by applying the Pythagorean identity of sine square x plus cos square x equals to 1. This will give us sine x minus 2 sine cube x plus 2 sine x. By changing cos square x using the Pythagorean identity, we will get 1 minus sine square x. This expression can be simplified into sine x minus 2 sine cube x plus 2 sine x minus 2 sine cube x. And we will get a final answer of 3 sine x minus 4 sine cube x, which is equals to our right hand side. For the second type of question, which we can encounter in chapter 4.5, we have questions which actually involved us to apply the concept of factorization in order to prove a trigonometric identity. Over here, I have an example of a question which is asking us to prove that tangent 2x minus 2 tangent 2x times sine square x is equals to sine 2x. While this question may look difficult at first, it is actually fairly simple when we apply the concept of factorization. How do we do that? Firstly, we begin by writing out the left hand side as tangent 2x minus 2 tangent 2x sine square x. We can see that the common term over here is tangent 2x. Hence, we can factorize it out of the entire term. And we will get tangent 2x 1 minus 2 sine square x. From here, we can see that we can simplify tangent 2x into sine 2x over cosine 2x. Similarly, if we look over here, we have 1 minus 2 sine square x, which we can simplify into cos 2x by using the double angle formula. From here, we can simplify the expression by cancelling the cos 2x and end up with a final answer of sine 2x, which is equivalent to our right hand side. The final type of questions which we can encounter in chapter 4.5 are questions which require us to involve the concept of multiplication in both the numerator and the denominator in order to prove a trigonometric identity. Over here, I have an example of a question which is asking us to prove that tangent 2x equals to 2 tangent x over 1 minus tangent square x. Like every proving question, we first begin by writing out the left hand side, which is tangent 2x. Now, let us change tangent 2x into something that we can work with, such as sine 2x over cos 2x. We can break up sine 2x over cos 2x into sine x plus x over cos x plus x. Why do we do so? We do so that we can apply the compound angle formula and get sine x cosine x plus cos x sine x over cos x cos x minus sine x sine x. By simplifying this expression, we will get a numerator of 2 sine x cos x over cos square x minus sine square x. Now, let us take a break and see where we are at. If we look at the left hand side, we are now at 2 sine x times cos x over cos square x minus sine square x. If we look at the right hand side, we see that there is only tangent. It seems possible that we can get the right hand side by dividing the left hand side with cos square x. So let us try that. By dividing both the numerator and the denominator with cos square x, we will get 2 sine x cos x over cos square x over cos square x over cos square x minus sine square x over cos square x. We are able to do this method as multiplying the numerator and the denominator gives us the same expression as 1. By continuing our proving, we will get 2 sine x over cosine x, which gives us 2 tangent x, and for the denominator, we will get 1 minus sine over cosine, which is tangent square x, which is equals to our right hand side. The final type of questions which we can encounter in chapter 4.5 are questions which require us to show that an equation is not a trigonometric identity. Over here, I have an example of showing that cos x plus y equals to cos x plus cos y is not an identity. The approach towards solving this question is to first use a counter example in order to prove that this is not an identity. What do I mean by a counter example? A counter example basically means that we substitute any value of x and y and prove that the left hand side is not equals to the right hand side. With this objective in mind, let us begin solving this question. First, let us write out the left hand side, which is cos x plus y. Over here, we similarly write out the right hand side and equate it to cos x plus cos y. In such an example, we can let x and y be any value we choose. However, let us choose an easy value such as pi over 3 and pi over 6. So for this question, I will let x be pi over 3 and I will also let y be pi over 6. Now, let us do substitution respectively and check if the left hand side is equals to the right hand side. Over here on the left hand side, when we substitute in both angles, we will get cosine pi over 3 plus pi over 6. If we evaluate this using a calculator, we will get a value of 0. Now, let us evaluate the right hand side and see what we get. Our right hand side will be cos pi over 3 plus cos pi over 6. If we simplify this expression, we will get 1 over 2 plus root 3 over 2, which can be simplified into root 3 plus 1 over 2. Now, over here, what we have gotten are values of the left hand side and values of the right hand side when we let x equals to pi over 3 and y equals to pi over 6. By comparing the left hand side and the right hand side, we can see that they are not equal. Hence, we can write a concluding statement that the left hand side is not equals to the right hand side. And therefore, this shows that this expression is not an identity.